Hello everyone, my name is David, and today I'm going to be talking about polar Kerr effect in CsV3Sb5 antimony. You can find more information on the archive paper linked below. So let me just flash you the names of all the people who worked on this project. There is a Aaron Capitolnik lab at Stanford, which measured the sample provided by Claudia Felser, and independently there is a Jing Shi's lab, and UC Irvine measured the sample grown in the Wilson's lab at UC Santa Barbara, and finally there is Ronnie Tamai from Würzburg who helped us on the theory side. Okay, so let me now introduce you the main character, the material CsV3Sb5 antimony. It was highly discussed in this March meeting. It was discovered 3 years ago. It's mostly known for being a Kagame metal, is a superconductor below the helium temperature, and more importantly for me, it has a property of charge density wave instability, which sets at about 94 Kelvin. So from right to left here, you see a high peak in the heat capacity, showing this is a first order transition. There's a kink in resistivity, and finally, more importantly, the plot on the left shows you a diamagnetic shift in the magnetic susceptibility. So what is known about this charge density wave? It's known that there are two possible two-dimensional configurations, so-called Star of David and inverse Star of David, which can stack differently in the third direction. So there are possible different variations of 2x2x4 and 2x2x2 charge density wave primitive cells. And I heard a talk yesterday which claims that they understand how it actually works. So I refer you to this if you want to find more information. More importantly for me, there is a different sort of evidence hinting that there is a broken time reversal symmetry in this material. There is a study of rotation of linear polarization, which could be explained as the time reversal symmetry breaking. There is a paper claiming that they see an anomalous Hall effect. Tangentially related, there is a very beautiful experiment on magnetochiral transport happening at much lower temperatures, and there is a change in the muon spin relaxation rate, which also happens at a different temperature. So I would like to answer a question. Is there actually a broken time reversal symmetry in this material? And to do so, I would like to test it by measuring the polar Kerr effect. So before we begin, we asked ourselves what is the best wavelength at which we can probe our material. And there is a highly pronounced Lorentz optical transition around 6,000 wave numbers, which is close to 1550 nanometers that we have in our lab, which we choose to test this sample on, in contrast to 800 nanometers that was used in the previously mentioned optical study, which doesn't have any optical transition. And indeed, as a sanity check, we see a sharp step-like feature in the reflectivity happening at this temperature, and we also see a linear birefringence change, which tells us that we are able to detect the charge density wave. So, but how do we actually test for time reversal symmetry breaking? So we do it by measuring the polar Kerr effect with this highly advanced and really cool apparatus, which was developed in our lab about 30 years ago. So we shine a light using the polarization maintaining fiber, which we phase modulate along one of the axes. And then upon reflection from the sample, we know that the right-hand polarized light and the left-hand polarized light will acquire different phase only if there is some sort of inert magnetism in the sample. By design, our apparatus is reciprocal, which means it's robust against any sort of optical activity, so it only gives a signal if there's actually a broken time reversal symmetry in the sample. And indeed, it was first tested on the well-known ferromagnet strontium ruthenate, which on the plot A here, you see spontaneous magnetization upon the cool down without the field, which actually changes from cool down to cool down, as you can see on the plot B here, because you have a different domain formation, and what we detect is the Kerr angle averaged over the beam spot size, which could be larger than the domain size. However, if you cool it down in the field, then turn the field off and take the data during the warm-up in zero field, you get the data as shown in the plot C, which gives you a Kerr signal several hundred times larger, and this happens because we now have a signal domain. So now finally, I'm ready to show you the main data. So first we measured the Kerr angle in the presence of magnetic field, and here on the left plot, I also plot the heat capacity data to orient ourselves in the temperature domain. And when we have a positive magnetic field, we see a negative shift in the Kerr angle, and when we have a negative magnetic field, we see a positive shift, which is fully explained by the diamagnetic nature of the sample. However, to test whether there is actually time reversal symmetry breaking, we want to see if there's any signal in the absence of the field, and to do so, we first cool it down in the field, turn it off, and then record the data in the absence of any field upon the warm-up, and we don't see anything. So this allows us to conclude that there is no actually time reversal symmetry breaking, and to further solidify our conclusion, we also measure it independently in the UC Irvine lab on an independently grown sample, where you can also see that they do not see any Kerr signal in the absence of the field, and the top plot here shows you the Kerr signal in the presence of the field. However, compared to the left one, they do not subtract the paramagnetic high temperature contribution, which is subtracted on the left for beta visibility. Okay, so this is the main result of our experiment, and to sum up, let me just reiterate that we studied the cesium antimony using the Signac interferometer to test for polar Kerr effect, and we do see a diamagnetic shift in Kerr angle in the presence of the field. However, we do not see any spontaneous time reversal symmetry breaking, from which we conclude that there is no inert magnetism. And however, if there isn't, for example, an antiferromagnetic order, it would not be sensitive to our experiment. We do not see it's possible because we don't understand how it would be, how it would show you a diamagnetic shift. So now I'm ready to take any questions, and thank you for your attention.